Thanks. Thank you, Akil. Thanks very much for the invitation to Chicago. So let's start by saying that this thing I will discuss today is part of a joint work. Big enough. Joint work with Anschütz, Bosco, Rodriguez, Camargo. And Scholze, which should be online very soon. And so let me start by first motive, kind of general introduction. So our work takes place in the context of p-adic geometry. We fix prime P for this talk. And while in p-adic geometry, maybe the geometric objects you primarily care about are rigid analytic spaces as defined by Tate, or some p-adic field like QP, for example, or CP. And so these objects are analogous to complex analytic spaces. A complex analytic space is something that you get by gluing holomorphic transition maps, like spaces which are like this vanishing locus of finitely many holomorphic functions in some complex open polydisk. And similarly here, rigid analytic spaces are obtained by gluing spaces which are associated to, which are the zero locus of finitely many rigid analytic functions in some affinoid disks. So of course, you have to take into account the totally disconnected nature of the p-adic topology to set up the series. So that's more complicated, but this is supposed to be really a p-adic analog of complex analytic spaces. But there are several important differences, and let me point out one. It is that, well, if you are over C, the local structure, so if you look at what your, let's say in the smooth case, so if I'm considering complex manifolds, then the local structure from the point of view of topological point of view, say from the point of view of singular or p-adic cohomology, is simple because you just locally it looks like an open polydisk, so it's contractible. But complicated in the even for smooth rigid analytic varieties. So if you take a point in your smooth rigid analytic space, and we take affinoid neighborhoods of this point, even if you make them small, still the étale fundamental group remains very large, and so the étale cohomology is still complicated to understand. So maybe this analog, this difference is somehow comes from the fact that maybe we consider p-adic étale, say p-adic étale or mod p étale cohomology as some kind of analog of p-adic cohomology over C. Maybe towards the end of the talk, I'll try to say why this is maybe not such a good analogy in some sense. But certainly you care about étale cohomology of rigid analytic spaces, and so that's the difficulty you have to deal with. But locally, things are not as simple as in the complex case.
Sorry, it's only the p-adic cohomology which is let's say for a disk, or
sorry, can you say again?
So my understanding is that the problem is that disk has is this true even if you consider let's say algebraic cohomology, where L is different from P?
No, for algebraic cohomology,
so it's only with
it's really with mod P for p-adic étale. Yeah, sorry, I should have made this more precise. And so I think an whole idea in the field, I think it goes back to work of Krasner, and then was used by State. Also, I think Fontaine, Bertrand-Berger. Later Faltings and much later Scholze is that things sometimes simplify after extracting many pieces. And so here, maybe more technical terms, the idea is that rigid analytic spaces are perfectoid locally for the pro-étale topology. Pro-étale topology is a finer variant of the étale topology, where you allow yourself to consider not just étale morphisms, but inverse limit of such. And so the idea is that your rigid analytic spaces, it always becomes perfectoid after a certain pro-étale cover. And perfectoid, well, roughly means that you can at least mod P extracts as many piece roots as you want. So to give an example of this phenomenon, a typical example of a perfectoid cover would be if you take, let's say, over CP, if you take the what corresponds to the ring of rigid analytic functions on the p-adic circle, then this maps to the variant where you have extracted infinitely many piece roots of the coordinate, and this is an example of a point covered by a perfectoid ring. You could also start with the type algebra in T plus minus 1 over QP, and then also add piece roots of 1 to replace QP by the cyclotomic extension of QP. Okay, but of course, when you look at it like this, it looks like you have not really simplified the situation in the sense that this is a nice Noetherian algebra, and you have replaced it by a very big CP algebra. But so the point of perfectoid spaces is that, well, the sense in which they are maybe simpler is that have a strong vanishing of cohomology properties. The idea being that if you have a perfectoid ring, you can transfer it to characteristic P, and then the condition of being perfectoid is a condition of being perfect. So you can, Frobenius is an isomorphism, and this property allows you somewhat to improve. Like if you have vanishing of cohomology up to some torsion, you can usually improve this to some kind of almost vanishing of cohomology. So, of course, if you are on an affinoid rigid space, by Taylor's theorem, you know that the structure shift has no higher cohomology. But what you gain by passing to the perfectoid level is you also get vanishing for the cohomology of the integral structure. And that's typically useful for this kind of motivation I started with. That if you care about, if you want to understand mod P étale cohomology, you can consider the Arthur-César sequence, where you take this integral structure shift, so this is the shift of inside the structure shift, the shift of 4 bounded elements. Which defines that is inside, and you model P. You're going to see that because of this Arthur-César sequence, you can try to rather analyze the cohomology of such a quotient. But then, if you start trying to do this directly on your rigid space, you run into the issue that, well, even if it's affinoid, then this has still a lot of higher cohomology. And so typically, if you, let's say you want to prove finiteness of a phi cohomology for, in the proper case, like Arthur-César did, for coherent cohomology of complex manifolds, then, well, it's not really possible to mimic such an argument, but it becomes possible after somehow you localize for the poetal topology and pass to the Perfectoid. So this kind of argument has been used by Faltings and Anschütz. As I said, for example, to prove finiteness properties of phi cohomology. Okay, and so now if you push this idea that you will work consistently, like locally for some very fine topology and reduce everything to Perfectoid spaces, this leads to this, Scholze push this idea really far, and this leads to the theory of diamonds and v-stacks. So let me introduce a definition. I will let arc stacks be the category of sheaves on the category of Perfectoid rings, the characteristic P. Endowed with the arc topology.
What is the secret meaning of the notation arc-stack?
So this is supposed to mean arc stacks.
Stacks. Was there anything stacky here with sheaves of rings?
Yes, so this is, I wanted to make a remark that I did not really specify which kind of sheaves we consider. Like I could, like in maximal generality, I could work with sheaves of infinity groupoids, but
so sheaves, but not necessarily
sheaves of sets. I think for the purpose of this talk, it's mostly fine to just.
An arc means what?
I was going to write it. So here you can see sheaves of sets or anima. Then you work with sheaves of animals, and maybe it's better to work with hyper sheaves. And so arc stands for arc topology. And here, a morphism of A to B of Perfectoid rings is said to be an arc cover. Gives the induced map on Berkovich spectra is surjection. So that's a very fine topology, which in particular is even finer than the poetal topology. So if you are familiar with Scholze's work, maybe the theory was mostly developed by him in the context of p-adic spaces, so using a variant of the arc topology called the v-topology. But for today, I want to maybe stay in the Berkovich setting, and so I will use always the arc topology instead. And so, like the way you somehow make this idea that you work consistently locally for this very fine topology and reduce to the Perfectoid case is by basically the following recipe. To X your rigid variety, you will attach a certain arc stack, which I will denote X diamond, which is a functor which sends A to an entity so it means like Perfectoid ring in, so X is a rigid variety over P. So A sharp will be some Perfectoid ring over QP with an isomorphism of the tint is A, plus a morphism from the Perfectoid spectrum of A to A sharp. And what M stands for the Perfectoid spectrum.
No, I mean as a space.
As a space, yes.
So you're giving an A sharp point.
I'm giving some A sharp point of this. Maybe I see X as a Berkovich space, everything rigid varieties. Example of Berkovich space. All right, and so what also proves is that I won't make this precise, but that this is a good replacement for X. Let me be very vague as far as, so to say, the topological properties of X are concerned. So, for example, they have the same étale side. So if you care about, that's what I mean, maybe by topological properties, if you care about étale cohomology of X with mod P or with QP coefficients, you can just formulate everything in terms of the corresponding parts.
Does it Langlands in the data?
Yes, it does. Okay, so that's basically the Perfectoid point of view on p-adic geometry, very quickly summarized. And so that's a very powerful formalism, for example, as I mentioned already, to prove some structural properties of mod P or p-adic étale cohomology of rigid analytic varieties. But it also has certain deficiencies, and I will maybe just mention two facts. This is just supposed to be general motivation for what comes next. First is related to like problems in like when you try to compare different series, a study cohomology series on rigid analytic varieties. We just said that passing to the diamond is like a good device to understand properties of étale cohomology. But you maybe also care about de Rham cohomology, and then you run into the issue that there are no non-zero differential forms on Perfectoid spaces. So you see it in this example. For example, if you look at dt, I'll pull back to this Perfectoid ring. I mean, this becomes like in this Perfectoid delta algebra, you can write T as a piece power for piece n power for arbitrary n. So you see that these elements becomes infinitely divisible by p, and so it's skilled with p. And so that's one issue when you try to maybe understand comparison theorems in p-adic Hodge theory between de Rham and étale cohomology, that this Perfectoid formulation, differential forms, never show up very like, there is no really natural way of making them. They do show up, of course, you can prove comparison theorems, but maybe not always arises from some local computations. And the other example I wanted to give is coming from representation theory. So I should maybe first say that there is a functor from the category of topological spaces to this category of R stars, which sends T something I will denote T underline. And this is sending A to continuous functions on the, maybe I should write it, topological space underlying the Berkovic space A, value in T. And so this, in particular, for example, if G or maybe H is a topological group, you can define an arc stack associated to H and try to do representation theory for G as we're studying certain categories of sheaves on this portion. And that's typically what happens in the work of Scholze.
Sorry, and when H under it's T underlined, it's not
Yes.
I.
That looks like yes. Maybe I repeat. So in the work of Scholze, typically you will be considering representation like classifying stacks of GQP, the QP points of reducible G over QP, and naturally appear inside some moduli stack of G bundles on the far fronted curve, and this way you can study smooth representations via sheaf theory. But if you start with H, like typically this example of like something of the form GQP, which has a structure of a p-adic group, then and you try to study representations with p-adic coefficients, then there are several classes of representations you may want to consider. You may want to consider like continuous representations, or smooth ones, or locally analytic ones, which you have Lie algebra action. And these are different categories of representations. But when you look at this object, when you use the formalism of arc stacks, this only someone remembers H as a topological group. Okay, so maybe for the first two classes of representation, you would be able to look up some sheaf theory for which you get these representations, but this one really uses this structure of p-adic manifold. And moreover, you'd like also to see how these categories of representations interact with each other. So you'd like to maybe not change your sheaf theory, but rather have different geometric objects associated to this different class of representations, then some geometric relations. And I don't really see like how to do such a thing using just formalism. So, and observe as well that this is not really an issue like perfectoid rings versus more general planar rings, in the sense that in the theory of like when you look at the p-adic groups, typically if it's compact, you may want to look at something like the spectrum of the ring of locally analytic functions. But if you take the Berkovic spectrum, the Berkovic space, or the adic space associated to such a ring, or the same for locally constant functions, they are dense inside the ring of continuous functions. And in Huber or Berkovic theory, the space that you get associated to a ring only depends on its condition. So somewhere you can't just using Huber adic spaces or Berkovic spaces, you don't really see the difference. This is different. Topological. So it's not just a problem of perfectoid rings versus more general rings. It's really, you need a geometry in which you can attach different objects to different rings without geometric objects without identifying them. And that's what we try to do. And so let me try to explain what is our geometric setup. Maybe first questions about this Okay, then if not, we try to let me start. And what I want to do is to give some kind of domain-precise idea of what the framework is, in the sense that I'd like to explain the definitions of the main objects, but allowing myself some kind of technical simplifications. So, I mean, don't hesitate to ask questions, but if you know some of this material already, you may notice that I'm kind of over simplifying it. I'm giving slightly incorrect definitions. So our geometric setup will take place in the context of Clausen and Scholze's analytic geometry. And I want first to briefly explain what this is. So here the idea is to try to do geometry in some various analytic contexts in exactly the same way you do algebraic geometry in some sense. So for this, maybe before explaining what the main objects in analytic geometry are, I should maybe recall how you could classically get schemes or stacks. Just because then we would imitate the process. So I would say that maybe you can decompose this in two steps. So classically, first you will define affine schemes. And one way, very cheap way of doing this would be just to say that the category of affine schemes is just the opposite of the category of commutative rings. So for me, all rings will always be assumed to be commutative. And then you can, well, if you want to define schemes, you have to be more restrictive. But if you take a maximalist approach and just try to define stacks as a big generality, you would just define stacks as sheaves on this category of affine schemes. Or some quotidian. So here you have some flexibility. First of all, whether you want to look at sheaves of sets or groupoids or infinity groupoids. And there it also you have some freedom in which topology you choose. Maybe Zavisky, étale, and so on. There are many options. But in general, you at least want to choose a topology. Maybe not always, but in most cases, choose a quotidian topology for which the category of modules, maybe a derived category of modules. So you want to have descent of quasi-coherent sheaves, so that as a consequence for any of your geometric object defined this way, it comes associated with it a certain category of quasi-coherent sheaves. So Clausen and Scholze in some sense mimic this procedure. And of course, in the algebraic situation, the first step was obvious because we know what commutative rings are. Although I think historically it was not obvious. We can do geometry with arbitrary commutative rings, but in the context of analytic geometry, it becomes more tricky. So you need to define what generalization of rings are. So that's the notion of an analytical. The pair A triangle TA, where A triangle is a condensed, light condensed ring So you can think of intuition is topological. Like topological rings, we give you examples of converged rings. And then you have the A certain derived infinity category, which is a full, so it will be a full subcategory of DA triangles. That's the category of derived category of condensed module over the condensed ring DA triangle. And it has, of course, to satisfy certain properties, but maybe I just mentioned, which is stable under limits and co-limits. And also contains A-triangle. Okay, so there are some other conditions that you impose, in particular to ensure that you have symmetric monoidal structure here. Basically, that's it.
Sorry, could you repeat? So A is which ring condensed?
A-triangle is a condensed ring.
Okay.
And then I give myself a subcategory of the whole category of condensed module. And here, intuitively speaking, maybe one should think to this as something like a subcategory of complete topological modules, or as this topological. That's maybe just intuition, because like it's also stable under arbitrary direct sums. Right? So maybe not directly fitting the usual intuition. But let's say because it's a subcategory stable by limits, under limits, the inclusion has a left adjoint, which you can think of as some kind of completion. Okay, and then you have a notion of a morphism between them. So morphism like between two analytic rings. Well, it's a morphism of condensed rings, which is compatible with this data. So in the sense that such that any M in TV, when you see it as an A-triangle module, whereas a forgetful functor is complete as an A. I will give examples. Let me first finish this main definition. So then you define affine analytic stacks just as opposite. So that an ring is a category of analytic rings, and then I just, exactly as I did before, define affine analytic stacks to be the opposite category. And then an stack, so is a category of analytic stacks. B is a category of sheaves. Then again, I don't specify. For on affine analytic stacks, which I endowed with a certain topology, which is called the Schritt topology. Part of the difficulty of this notion of analytic stack is getting the precise definition and properties of this topology, but I don't want to go into. I maybe just again in terms of intuition, just say that it's in some sense the finest topology, p-adic topology, for which one has descent of this category of complete A modules, plus of the 6 operations one can define. And so in particular, as a consequence, that's what I want to remember. If X is an analytic stack, associated to it, there is a certain category Tx, infinity category symmetric monoidal of quasi-coherent sheaves on X, which is such that if X is affine, it's just this category TA, this part of the definition. That's pure notation, not. So here, if I think to an analytic ring as an affine analytic stack, I will denote it unspec. That's just notation. All right, so that's about analytic stacks. So let me give 2 examples of analytic rings that are relevant for. One basic example is some analytic ring structure called QP solid on the ring QP. So let me see QP, it's a topological ring with its natural topology. I see it as a condensed ring. And then I need to specify a category of complete, which will be called in this case solid QP modules. And in this case, it happens to be, it's a derived category of some abelian category. Some abelian subcategory of just a category of modules over the condensed ring QP. And it has one compact projective generator. Which is given by, we'll call it P. It's a countable product of copy of TP, and then I will. So it's an abelian category with one compact projective generator. So it's entirely describes it as a category of modules over the endomorphisms.
Maybe what is the ring of endomorphisms of this compact generators?
Right. So if you
endomorphism of this models and the usuals
in the category of condensed.
But suppose I don't know what condensed is, then is there a?
I can write a formula.
Also, like it is a topological. In this case, it is.
Yeah. So I'm looking at. So it's the same as endomorphisms. Yeah. So. It is right. So it will be products of direct sums. That's.
I think you tried to say something. Can you repeat what you said?
Yeah, but well, I was going to say, if you want some sort of p-computed drives.
Oh, yes.
Yeah, I would just say that it's in this case it is. You can think of it as an ordinary topological module. So you have product topology on product of CPs, and then covalent topology.
So you consider P more or less naive as a differential module. You consider its endomorphism model, and then the whole category is category of model with right?
I mean, there are other, that's maybe not how the definition proceeds,
But it's a true.
but it's a true fact. And yeah, so one can also describe them in a different way, which maybe looks less artificial. But as well, as for any analytic ring, as part of the claim, that this category will be like contains stable under limits and colimits. So it also contains, I wanted to point out that it contains QP Banach spaces. But also limits. So for example, Fläche spaces or colimits of some. And I should say that here colimits are, if you look at the underlying set, it's really the naive, like uncompleted colimit. It's not like a Banach space colimit. It's really just like, for example, a direct sums of copy of QP, arbitrary direct sum is also an example of solid QP. So that's not completely obvious from the definition. You need to see that you can write Banach spaces as in terms of limits and colimits of this compact generators. That's true. And the second example is kind of a little bit empty. It's just to say that once you have one analytic structure, you can cook up others. That's the notion of an induced analytic structure. So if R is a solid algebra, so solid as a QP module.
Sorry, and solid means roughly non-Archimedean. But I remember that there are solid liquid maybe gaseous. So, and I think solid graph
Solid, roughly, yeah, solid is something like non-Archimedean. In the sense that, well, you can look at, in this condensed world, you can look at, like someone, if you do, maybe even in the category of condensed abelian groups, you can look at the following. So this is like the free condensed abelian groups on this profile set, which is a compactification, 1-point compactification of N. That's something which is usually denoted P, but I already used the notation. And so if you have the condensed module M, so you can look at morphisms from these condensed abelian groups towards M, and this is something like the space of null sequences. In M, because mapping from there is like just a sequence with a limit, and I kill it out corresponding to infinity. So it's a sequence converging to 0. You have to be a little bit careful with this intuition, because even if M comes from a topological abelian group, if it is non-separated, like this is not really a subspace of the space of sequences in M, but that's some intuition for what this thing is. And there you have some operator which is identity minus shift. And being solid is the same as saying that this endomorphism is an isomorphism. And if you think of what the inverse, so if you have a sequence xn, I would be saying sending by this identity minus shift to something like xn plus 1 minus xn. And if you try to construct an inverse, you see that it's given by sums, like partial sums of the sequence. So saying that it's an isomorphism is telling you that any null sequence is summable. And so, okay, know that I explained this for condensed abelian groups, so Z modules, and that's very different from what I said upstairs. But this solid structure on QP is in fact a special case of what I would say, hey, I mean, it's an example of an induced analytic field structure. So by definition, a QP module is solid if it is as a condensed abelian. So it defines this subcategory. So that's in this sense that this notion of being solid is supposed to be something being non-Archimedean. So for example, if you take the real numbers and you solidify them, you get 0. So the next example was if I take R to be a QP algebra, which is solid as a QP module, I have a certain induced analytic field structure, which I will denote as this. That's supposed to be a subscript. And so R is my underlying condensed ring. And then I look at the condensed R modules, which are solid as QP. So that's what is called induced. And in this talk today, I want to only consider analytic induced analytic field structures from QP3. So I'll be doing rigid geometry in some generalized sense. I will be considering some banal or more generic class of topological QP algebras. But I will always just endow them with an analytic field structure which is coming from QP3. So that's very close in terms of maybe again intuitively. There is this difference between two different geometric setups for p-adic geometry, Huber-adic spaces and Berkovich spaces. And here in Huber-adic spaces, one always also carry, in addition to a Huber ring, a certain subring of integral elements. And the way Clausen also interprets this datum is as a way to specify this choice of R plus is a way to specify some analytic structure on R. In Berkovich theory, you disregard these higher round points. And so in some sense, the fact that I started the talk in the Berkovich setting is not in the usual maybe adic spaces setting, is because I want to make this restriction. And so this has one advantage, which is that it makes certain things technically easier. So for example, I have A and B, some solid QP algebras. And I consider morphism between them, so that I want to see it as a morphism of analytic rings with the induced structure. Then I had this notion of a strict topology, which I did not define precisely. But in this situation, being a strict cover is the same as saying that the morphism A to P is descendable. Which is a notion that was introduced by Aki. So meaning that A belongs to the top category of TA, which is generated by dB under finite limits on vectors. So an example of a descendable cover would be maybe with several, not just with one rings, but if you take an open cover of the rational localization of the vertical space of A, then you can write the Hodge complex. You see that the ring of functions on the space is like a finite complex of the rings of functions of the localization. Okay. So at this point, it may look like a possible geometric framework for doing the p-adic geometry we want to do would be to work with analytic stacks over cubic solid, but with induced analytic ring structure everywhere. But this is still too big. Maybe even if you restrict to test objects which live over cubic solid. And again, let me make the analogy with Huber theory of adic spaces. In Huber theory of adic spaces, you have rigid analytic variety that you can see as adic spaces, but you also have schemes and formal schemes. And they behave very differently. And the main difference between the two classes of Huber rings that you get in this way is that the rings coming from rigid geometries are tight. They have a pseudo topologically important. And for this project, we really want to do some kind of rigid geometry. And so we want to disregard examples like we want a class, more restricted class of rings. That's solid algebras. Containing like rings you encounter in rigid geometries, so maybe more generally plate Huber rings, but not something like QP, like what corresponds geometrically to the algebraic affine line. So the QP bracket C was a polynomial algebra property that's just as a QP module, direct sums of QP of QP. So that's solid as a QP. So that's an example of a solid QP algebra. But we want to somehow that the version of the affine line that we use is really this analytic affine line, not the algebraic. So we want to restrict more our class of the rings that we model the geometry. That gives me so like A solid QP algebra. So this is definition in several parts. So first, let me define certain subsets. Random subset. So let me pick a number, non-negative number, R. One can define A less than R, a certain random subset or subanima if you work with native rings. A less or equal to R, which is supposed to be the subset of elements of norms less or equal to R. So how do you make this precise? So at the level of underlying sets, the idea is the following. So if you have some functions A, some element of A, it corresponds to a morphism from the Tate algebra, from the polynomial algebra in one variable to A, just by sending C to F. You'd like to say that F has norm So maybe that's really, I should really write that. So F is an element of the underlying set. Okay? We will say that F has now less or equal to R if this morphism extends. So QP algebra, which is this is just this is a ring of over convergent functions. On the disk, the affine disk. Right, so morally, the element has norm less than R. It means I can evaluate any such function of it, and this gives me something well defined. The idea work with other convergent functions for a reason discussed, but also let me point out that this actually this algebra is idempotent over this one. So it's really unique. Like this extension, if it exists, it's unique. So in general, that's not enough really to define this as a convergent subset. You just define a subset of the underlying set of A. So to define it properly as a condensed subset, really need to specify the values what A is what R is evaluated on any S line to finite. And so this definition we propose is by like defining for this. I won't do it. You define a certain something not in this, which is to be thought as over convergent functions again on the S, something like the S-dimensional disk of waves, which of course is not a meaningful statement. If S is just a finite set, that's just over convergent disk of dimensions. You kind of need someone to define some kind of S families of such, and then you just mimic this. See? You have morphism from S to A. You say you want it to extend. You say it lands in this if the morphism extends. Okay, that's a. So in particular, A, just point out that A less than 1 is a subring. Not just a subset, but a subring. So if A was just a usual banner, it would be algebra. Yeah. A less than 1 is a subring of power bounded elements. For arbitrary R. Okay, so now we say that the ring QP algebra A is bounded if A is in fact just given by, okay, take the subring and then you invert T and you get. So you want to have natural map from right to left and we want this to be nice and officer. And here the intuition is that any function on F is bounded. Any function maybe in unspec A. Because what that equality means is that if you take some That's when S is just a point again. It means that you have some elements in the underlying set of A. It's saying that it comes from here. It means that the morphism. So if you have F corresponding to the simplest case, this is the point. If you have a morphism like this, saying it's bounded, so saying it belongs here means that there exists some N big enough such that F extends necessarily uniquely to a morphism from some Tate algebra.
Just a quick question. So one question is, in the remark, do you get exactly the power bounded elements, or in the remark, do you get exactly the power bounded elements, or elements spectral radius in that much one? Is that the same as being power bounded?
It's the same thing, right? I'm a bit worried about non-uniform corner rings, but I sort of checked.
I also think at some point we should take a break.
Yes, so maybe I just finish the definition and yeah, I can just, and then I will give examples. So the main class of rings we will work with is what I will define now. We say that A is Gelfand. If A is, well, first of all, you have to be bounded. And the uniform completion of A, which is defined by, I take this less or equal to one part, I take its p-adic completion. And then I invert P again. And I want this to be a Banach. Yeah. So really the content here is that a priori, another way to say is that I model the A less or equal to one part is that this is discrete. So a Banach QP algebra is, I should have recalled what QP Banach space is. It's something which can be written like this, where W0 is P complete, and W0 mod P has discrete distribution. That's really the condition that mod P is the same as discrete. So that's what we call Gelfand rings, and after the break, I will give.
Why is it called?
So I think the reason is so you have a map like this. You can always get a map from. Well, first of all, there is a way to make this to work with respect to as a topological set for any such solid map. And you would like some kind of Gelfand transform sending an element of A to a continuous function on the Berkowitz spectrum. But to really get this as a morphism of condown strings, maybe you get a morphism just of rings, but to promote it to a morphism of condown strings, it seems to require a condition.
But why is R there? R is a real number, so what?
It's because like this is parameterizing norms.
Because it's norms.
So roughly here it's F goes to something like I have the norm point S of the vector spectrum. Not automatic. Satisfy converses. It's not an if. I don't think it's an if and only if, but at least if you know the ring is Gelfand, then you have this. the terminology comes from Justin Clausen, but in the complex case. So we just wrote terminology. Maybe I do a break now.
So we'll have a 5-minute break.
We may start. We give examples of non-examples of Gelfand rings. Examples of Gelfand rings are now the uniform. What are examples of Gelfand rings? But also co-limits of such. So, for example, what's uniform? Uniform means well, there are several equivalent characterizations. One is that the topology, like the spectral subminor, is norm and induces the topology of formalism.
Spectral subminor.
Subminor is a norm, and it induces the topology of subminor. Another way to say that the subset of power bounded elements is norm. So co-limits of such, like this category of Gelfand rings is stable under co-limits in solid algebras. And so typically, maybe what I want to remember is that like rings of functions or say affinoid disks or over-convergence disks will be examples of Gelfand rings. So let me also give two non-examples.
I wish if you could say briefly why the condition is stable under cohomology. That's all.
Yeah, I'm not sure I can give you very good. So the uniform for filtered colimits, for example, the uniform convection. It will just be the Banach, the colimits as Banach spaces. So non-example would be T. So polynomial algebra in one variable. Well, this one, because already it's not bounded. So here, the element T inside QPT is not bounded because, well, this property that extends to state algebra, just not true. But asking moreover that you have something Gelfand, it also excludes examples like this one. Something like bounded functions on the open disk. This is also, this one is bounded, but it's not Gelfand. And here the reason is, okay, the power bounded part is just CP double brackets T, but when you mod out P, it's like FP double brackets T with a p-adic topology. So this is not discrete. but that's in some. We will see that it's also something we will have. Should something we want. Somehow that this is not an example which is allowed. And so we define now the category of Gelfand stacks as the category one. We just mimic the definition of analytic stacks, but we restrict our test objects to be Gelfand rings. So the category of stacks, of sheaves, on the category of Gelfand rings with just the topology, the same shape, which, because as I already explained, I always take my analytic ring structure to be induced from QP solid, so it's just the same as the descendant. So that's really the category of geometric objects with which we want to work. And maybe I need to make two remarks about it. The first one is that there is a, so it's of course natural to wonder how, so I explained what general analytic stacks are. Now I'm introducing some other category of stacks. It's not completely clear to me what the exact relation is. So you have a functor like this, colimit preserving functor, which sends spec A to spec A. Here I'm using the same kind of purely notational. This is just supposed to mean the Gelfand stack, affine Gelfand stack attached to A. And this I can just realize and put an stack like this. And this functor has the right joint. Gelfand, this. And let me just tell you what it gives when you apply it to these two non-examples. So in analytic stacks, I certainly have an spec of polynomial algebra. It's something you may think of as algebraic affine line over QP solid. So I said that this ring is not Gelfand. And what happens when you take the Gelfand modification? You get, well, you get analytic affine line seen as a Gelfand stack. So what is this? It's by definition the union over all n of G spec of functions of the Tate algebra. So an increasing union of this. And these are Banach QP algebras, these are examples of Gelfand rings. So that would already be true if I was using just bounded rings. Basically, kind of this condition that A bounded is forcing that would be the functor of represented by the affine line on the left, that the affine line that's the thing which is represented by this analytic affine line. Asking that they coincide. And similarly, you can describe an spec of these two algebra C double brackets T one over T. And this is the open unit disk, rigid analytic open unit disk over QP. Again, a non-affinoid, non-quasi-compact space. It's an increasing union of units. So not for the first example, if you have maybe scheme over QP, I guess like the corresponding Gelfand stack would be just the analytification. And this example suggests, but fully check that if you start with a formal scheme over P, like typically this one is P double brackets T, which is not p-adic, and you take its rigid generic, this generic fiber in Gelfand stacks, so you base on QP, and you take the Gelfandification, you get what is called a Berthelot rigid generic fiber. So, yeah, so maybe that's probably a more general statement behind. So you see that I give this example to show that really working in Gelfand stacks is really doing some kind of rigid analytic geometry, which is what we want. And the other part of the remark is that the category of Gelfand stacks contains fully faithfully the category of well, Dagger rigid spaces, ordinarily Dagger rigid spaces. Dagger rigid spaces are like the versions of rigid spaces where you replace the data algebra by the overconvergence. So examples we maybe care about in p-adic geometries, they can be realized fully, still as a full subcategory of this category of Gelfand stacks. Okay, so now let me provide maybe a slightly different perspective on this by pointing out a key property of Gelfand rings. So one has the following proposition. So if A is a Gelfand ring, there exists A to B descendable such that B is what we call a nil perfectoid. What does that mean? This means that, well, first I should have maybe remarked. So maybe I put it here as a parenthetical remark. So I should have said it before. A is bounded. That I think was Juan's main motivation for this definition. Then you see that A less or equal to 0, which also makes sense. Some of the element of non-zero. This defines an idea. Roughly speaking, if you multiply a bounded function by a function over convergently close to 0, it remains over convergently close to 0. And so this means that for my B here, being Gelfand, it's bounded, so I can form this quotient. So that's this thing is called Dagger hierarchical. The condition being nil perfectoid means that this is a perfectoid ring. Perfectoid always means perfectoid plate. In this case, it will also be the same as the uniform condition. Right, and so now, subclass of Gelfand rings, nil perfectoid rings, they are not stable under arbitrary.
B is not Gelfand.
B is also Gelfand, yeah. So, I mean, the nil perfectoid rings are examples of Gelfand. In this case, basically the difference is that uniform completion is not just some arbitrary binary QP algebra, it's a perfectoid Tate algebra, and moreover, it coincides with just stagger reduction. They are stable under short. And so in particular, this means that we could have defined this category of Gelfand stacks using instead not arbitrary Gelfand rings, but just nil perfectoid rings. They form a basis for the topology, for the descendable topology. So let me give some example of nil perfectoid rings.
Sorry. So this B quotient b-adic, B quotient b less equal to 0 equals bu. That's part of the definition.
Oh, that follows from the fact that this is assumed to be.
I see. Okay.
So in general, this quotient injects always into uniform completion, but then it happens to be already on. So perfectoid rings, of course, are examples of Gelfand rings. Are nil perfectoid. Let me give a non-perfectoid examples. If you take CP, write it like this, CPT dagger, it's a co-limit of functions, Tate algebra in T about P to the n. So that's like functions which are defined on some over-convergent neighborhood of 0. This is a nil perfectoid. Well, in this case, I call this A as this dagger reduction. So this quotient is just P. So T is an example of a nil of an element is a dagger nil radical. This dagger nil radical is not nilpotent elements, it's really elements which are sometimes topologically nilpotent. So there are, in this case, you see that by forming this co-limit, I make T arbitrarily divisible by P. So the norm of P must be specific. And last example, maybe if A is a Banach P algebra and B is some quotient, and then I can look at the bounded by one part, that's a CP. So P complete thing, and then I can take the perfectoidization to the sense of Pat and Louis. Derive P complete. Or maybe I want maybe it's, let me say P complete. Right. And then I invert P. And that's, so what is it? It's like this B would be like a semi, like the bounded by one part to semi-perfectoid ring. And what am I trying to say from this? I wanted to say that this is this one is perfectoid and this is the same. So this means that this B will be. So in other words, like semi-perfectoid rings, like generic fibers of semi-perfectoid rings, are examples of nil perfectoid. So you can also imagine that nil perfectoid rings are some generalization QP setting of semi-perfectoid rings.
If you take an element that maps to 0 and the perfectoidization is more of 0, so you have an incomplete ring. And you have an element which maps to 0 and the perfectoidization and on generic fibers it's sort of norm zero in a sense. Is that correct?
Yeah, so I'm claiming that this morphism is subjective. That's what means. Because they have the same Berkovich space, so some of the ideal is defined. The kernel is an example of the diagonal photon. Okay, so because of so that's maybe another perspective. You can imagine it's like using semi-perfectoid rings in the context of p-adic formal schemes. Nil perfectoid rings will play the same role somehow. And this also shows that we could, in some sense, this notion of Gelfand stack is in some sense as close as possible to arc stacks, which would be functors on perfect rings, but where we allow some kind of diagonal nilpotent sequence. We prefer to somewhat define them as functor on all Gelfand rings because, well, there, for example, that's convenient to see that you can realize these rigid spaces or Berkovich spaces as Gelfand states. But we could have just done everything directly with it. I wanted to discuss some applications. Yeah, we can discuss it. Sorry, this will be also good. So when you pass through uniform completion, you kill the diagonal. So are there other questions about this? So part two, I want to discuss how we practice.
Can I ask a general question?
Yes.
So in a lot of these examples, are they when you say stacks, are they like portions of a no perfectoid ring by some equivalent relation that's self-representable by no perfectoid rings? So I was wondering how far in these examples, how sort of generally you have to go into the stacks. So like in algebra, in the algebraic setting, you consider stacks that are quotient stacks seen by a group of this equivalent relation. I was wondering if that's together.
I think at least for the Rham stacks, that would probably be. So the first application, like use of this framework is to develop a series of de Rham stacks in rigid geometry. More generally, one of our goals was to define some notion of prismatic cohomology for rigid analytic spaces. Another application is in the context of geometrization, like doing a p-adic analog of the work of Hodge, geometrization. So today I will just discuss point one, maybe say, probably not, but maybe something about point two. And okay, Thursday in the number theory seminar, I'll try to explain rather this task. So for today, let me just maybe focus on this theory of analytic. So the toy model for the definition of so we want to define some notion of analytic de Rham stack associated to a rigid analytic space. And so the toy model for this our construction is the following characteristic P examples. So let's say you consider it's just toy model, so maybe like exact setup is not so important here. Something like sheaves on p-algebras for the, let's say for the descendable. And I will introduce a perfect variant where I do the same, but I only consider perfect. For the same topology. So what I have is I have a restriction functor. If I have a functor stack which is defined on arbitrary FP algebras, I can just restrict to perfect FP algebra. And this functor, it has the left and the right adjoint. So the left adjoint is a thing which sends I have R perfect the algebra sends to R. The right adjoint is something that deserves to be put to the Rham stack. So it's maybe not the Rham stack when we classically use it. It's not that. So by definition, it would be the so X de Rham R X is a stack on perfect algebras. X de Rham evaluated on R will be X of the colimit perfection. Right. So if I take R, some FP algebra as a functor co-represented by it, functor co-represents, sorry. I take R, some FP algebra as a functor co-represents FP algebra. So that maybe not quite the usual de Rham stack. So first of all, there are more, even if there are characteristics here, I do not consider like divided powers. But also maybe usually the Rham stack, even forgetting about divided powers, usually the Rham stack is maybe defined by usually you would maybe imagine that it's something like R goes to X evaluated on the reduction. But that's a sheaf for the Zariski or étale, because if you sheafify for something like the C or the descendable, so here I don't want to sheafify descendable. Even if it would be enough, then what happens is that for semi-perfect rings, which form a basis, the perfection on the reduction things. So locally for my topology, reduction and perfection are the same. And moreover, if X is a shift, then this formula already repeats. It's not yeah. If I look at it, I see my perfect. Okay, so this is procedure we want to mimic over QP. Right, so we will just do the same. So over QP, we have this similarly a restriction factor. So the characteristic P, this restriction factor was perfection. So I will call it perfectoidization in this context. And I will denote it with a diamond. And what's the source, what's the target? So it's a factor which is defined on Gelfand stacks. We take value in the category of hard stack over QP. Maybe I should say, yeah. Maybe I will note like the Scholze notation M-R-Q-P for the factor which is over the constant. Maybe. The P just right like this, and this is the arc shifts on perfectly rings for all right, so basically, if I have functor here, it's like a functor defined in all Gelfand rings. Perfectly rings are examples of such. I just use Gelfand arcs. There are some implicit claims there, but if I start with something which is shift there, it will shift over there also. So to make this work really properly, we actually need, I should maybe have said before, we need to put some mild restriction on the class of Gelfand rings we consider. So they have to satisfy some topological countable generation property. And they also have some satisfy some kind of mild finite dimensionality properties. But I will just know this technicalities. And so now this has left on the right adjoint again. And the right adjoint is what we call the Analytic de Rham stack form. And you note so the piece of notation, if X is a Gelfand stack, I will just write X de Rham. So X de Rham is not a priori well defined, but what I can do is, that's the definition, I can take the perfectoidization. So I have the Gelfand stack, I see it as an arc stack, and then I apply the Rham stack. That's just convenient notation that I will use. So in terms of factor of points, what you have, I don't have a description on arbitrary Gelfand rings, but if A is nil perfectoid, then I have that X de Rham evaluated on A is the same as X evaluated on A, which is also the same nil perfectoid case as this thing. So it's a bit analogous to what we had before. There is some restriction. It's not for arbitrary Gelfand ring, but at least on this basis of topology, you have this formula. one remark I can make here is I explain the characteristic P analog of this construction. It also has an Archimedean analog. Maybe it's useful in terms of intuition. In the Archimedean case, the role of perfectoid rings, like what plays the role of perfectoid rings, are spaces of continuous rings of continuous functions on profinite sets. Continuous functions with complex values. Why is it a reasonable analog? Well, perfectoid rings, in fact, you can usually, when you work with the arc topology, you can localize further and find any perfectoid ring admits an arc over by something which is called strictly totally disconnected perfectoid ring. So that means that in particular the Berkovich space is profinite, and plus some conditions that the residue field are algebraically closed and constant. Over C by Gelfand-Maser, you have only one possibility for the residue field. It must be C. So this somehow, maybe here really the correct analog is strictly totally disconnected perfectoid ring, which can always reduce to for the arc topologies. They are really supposed to be analog. And then the category arc stacks, so what should be what plays this role is the category of condensed sets or condensed anima. Which are just some kind of generalization of topological spaces, and the perfectoidization, analog of the perfectoidization functor, is just something like taking the underlying topological space. That's the analog of the de Rham stack is taking the Betti stack. Something which lives over C, but based on C. So there is this functor from condensed anima, so let's say topological spaces, to analytic stacks, which is called the Betti stack functor, which in the profinite case is this profinite space is just unspec locally constant functions. But some kind of incarnation, stack incarnation of some version of Riemann invariant. In this case, the de Rham stack is just
the analog of Gelfand stacks in your convenient set.
So you could define some category of nil perfectoid rings as nil dagger sequencing such. I don't know if like certainly I don't know, like probably there is also notion of Gelfand rings, but I'm not sure which one. Well, it's just some kind of analogies. What I want to say, really useful. And so let me state the theorem what we prove about this de Rham stack construction. First of all, we show that this functor commutes with limits, limits. It's a right adjoint, so commutes with limits, but it also commutes with colimits. In particular, it preserves epimorphisms. Maybe I post right in the comment. If X is partially proper rigid space, the natural map. So you always have the map from X to X to R. For example, well, because of I see my rigid space, partially proper rigid space as a.
So what is partially proper?
It means that it satisfies the derivative criterion for properness. So yeah, so for example, the Stein space, I can basically kind of affinoids or proper rigid space. The example. So it's just this technical restriction because of the fact that we work with this. So yeah, I was saying that here when I write this, I'm implicitly thinking of X as a Gelfand stack, as I allowed to by what I explained previously. And then this map is just coming from the unit of this adjunction with perfectoidization on the Rham stack, or also more completely just from this explicit formula for the points. And the claim is that in this case it's homomorphism. And you can describe the Chechner of this geometric realization of so you take the fiber product of its cell and you take the over convergent completion along the diagonal. You have the diagonals sitting inside this fiber product, and you take the over convergent neighborhood of the diagonal. Maybe that's something I would should just maybe just write like this. So something like takes the diagonal inside X, takes some over convergent neighborhood. So, for example, if X is A1, I find line analytical from line, then this de Rham stack is A1 analytic modulo. Well, in this case, it has a group structure, so it's just something I will call GA dagger acting by translation, because GA dagger has a spectrum of these algebras that are here. Just over convergent function around it.
So I see that x, what is x n plus 1? Yeah, so x cross n plus 1 over x minus 1. If you read the formula, what is t delta x?
Yeah, so it's supposed to be a dagger.
It's a not. So you see, this is the level of my question. So
you have the diagonal inside x times over spacular times itself. Then I'm taking the over convergent neighborhood of the diagonal inside this. That's what I denote.
So you get the over convergent neighborhood of the diagonal in the power of x, and then is it a colimit with respect to n or with respect to
yes. Basically, I was trying to just describe that by the product of x. The terms it's a judge now.
So naive would like to say that x de Rham is closure of x by a certain equivalence relation, and let I say that x two points are equivalent and they are infinitely close. This would be the naive definition. And are you saying that this what is the relation between this colimit and this naive thing? Suppose X is nice.
Yes. In this case, I think it's really just given by this form. So I'm just, that's what you said. So I take X and I look at the equivalence relation inside X times X, which is given. So the difference with maybe the other versions of the de Rham stack is that instead of taking the formal definition, so identifying infinitesimally close elements, I want to identify elements which are over-convergent.
But then why? So what I said was probably too naive. So you want to consider all this. So what I just said is my suggestion, main suggestion was to consider a small neighborhood of the square, but you insist consisting small hours. Does it really make a difference then?
I would, yeah, I think for sheaf of infinity cohomology, it should make a difference. If I take just X to be, say, a sheaf of sets.
So if X is a sheaf of sets, then it's no difference. This is because we want to do sheaves.
Sorry, maybe I should have, I don't think one lose much by just taking sheaves of sets. Maybe I should have told this. Yeah, so that's, yeah, maybe important formula is this one, and that's to show that, so point one is somehow, in particular, proving you should think to it as saying that the de Rham stack has very strong descent properties, like epimorphisms of arc stacks induces epimorphisms in de Rham stacks. Point two is supposed to tell you that this de Rham stack for nice Gelfand stacks, such as partially proper rigid spaces and type objects, they are just yeah, sorry, I understand the confusion was okay. I have a more general statement for derived version of Berkeley spaces for which one. We need to write this, but for partially proper rigid space, certainly this formula is enough. And it's supposed to tell you that the de Rham stack defined in this way, this abstract way, is doing what you think you should do if you are familiar with the de Rham stack, up to replacing formal completion by over-convergent completion. So that's why it's called analytic de Rham stack and maybe not algebraic, just de Rham stack. And in particular, this allows one to show that in this situation, maybe it's furthermore as smooth, the cohomology of this analytic de Rham stack is de Rham. So also explain why it's called the de Rham stack. And you can also show that F is smooth morphism. Arc stacks. Then so induced morphism of the de Rham stack is cohomologically smooth. And you can also there's a description of the generalization. So of course, one advantage of this formalism of analytic stacks is that once you have defined something as an analytic stack, then in particular, as I explained, so this also holds for Gelfand stacks, it comes equipped with a category of quasi-coherent sheaves and 8 with a 6-functor formalism. So 3 is an instance of like applying this to the case of the de Rham stacks, and for getting application, like some, for example, Poincare duality or analytic modules, that's the kind of statement you need to. I wanted to give another example. So I gave the example of the affine line, but you can also look at the example where it's just the affinoid disk. And then you can describe the de Rham stack. And in fact, in this case, the map this is not partially proper, but you can look instead of the over-convergent disk, which is containing this one, just the limit of disks of radius strictly bigger than 1. And now they have the same de Rham stack, and now you can somehow use this kind of statements to show that this is again explicitly described as something like this. So p-adic again is acting by translation of this over-convergent disk. This is the Rham stack for the affinoid disks. So as a conclusion, in this case, cohomology of the de Rham stack is in fact computing for you not the de Rham cohomology, but over-convergent. Which is a good feature because it's well known. The Rham cohomology of the affinoid disk is sort of pathological, as well, so H1 is very big and non-separated and so on. But when it's also well known that when you go to the over-convergent version, it kind of kills the Rham cohomology groups. Okay, so I take 5 years or should I stop? Yeah. Just let me try to say one last thing about this de Rham stacks. Well, what is the point of maybe defining the de Rham stack like this and not as an explicit function like that one? Well, one advantage of this definition is that you see that it makes sense for any arc stack, which may be a bit surprising. So X de Rham, by definition, makes sense for any arc stack of octopus. For example, a Perfectoid space. This for me was a bit surprising because you think of sheaves on the de Rham stack as some category of analytic modules. That's this what happens for rigid spaces. And it's not clear why you have such a notion for Perfectoid spaces, because as I explained, there are no differential forms in Perfectoid spaces. Also, arc stacks, you are gluing things for a very fine topology, and it's not clear for which modules to make the sound and so on. So it's a priori not so clear why such a thing, why you can speak of analytic modules on any arc stack. But one way to use this flexibility is the following. So let X now definition. Let X now be any arc stack. So no, I don't assume it lives over QP. Just on as at the beginning of arbitrary Perfectoid ring of character. And then what I can form is I can consider the following stack, which I call the Yudokato stack. Each case stands for Yudokato. What I do is I simply base change arc stacks. So this is supposed to denote arc stack associated to these rings in QP. And then I take, so after I've done this base change, I get some arc stack leaving over QP, and then I form the de Rham stack. So if X is perfectoid, sorry, I forgot one step. There is a natural Frobenius acting on X, like on any arc stack, because it's a functor on perfectoid spaces of characters P. And I want to mod out by this, some kind of partial Frobenius, and then form the de Rham stack. So if X was perfectoid, so just arc stack associated to a perfectoid ring, this would be this thing here. Also, it takes the quotient by Frobenius. This would be, in fact, the arc stack associated to the Fark-Fontaine curve relative to this. So you can think of this Yodo-Kato stack as something like the de Rham stack of the far quantum curve over X. Except that for arbitrary X, this is not a Berkovich space, it's just some arc stack. And right, so what we expect is that this is geometrizing, justifying its name, as construction which is a setting of, okay, so expectation, so if X is the arc stack associated to a scheme in characteristic P, then we expect that the Yodo-Kato stack is, in this case, geometrizing rigid cohomology, in the sense that its cohomology, its coherent cohomology should be rigid cohomology. But if instead X is an arc stack associated to a rigid variety of a QP, then we expect that this is geometrizing the thing called Yodo-Kato cohomology, which in this generality has been defined by Scholze and Lisian. Last thing I want to say is, so this cohomology theory of Scholze and Lisian, if say X is giving, let me do the geometric case. If X is over CP, Yodo-Kato cohomology, it would be complex of phi n modules over the maximal and ramified extension of QP. And what does that have to do with this static construction? Well, something we can prove is the following theorem. So there is an equivalence between category of vector bundles on, or more generally, even perfect complexity, on the Yodo-Kato stack associated to CP, which CP being perfectoid is really the de Rham stack of the far quantum curve, really the originally first defined one. Well, we show that this is precisely the category of phi n modules. So you see that if X lives over CP, I take the corresponding Yodo-Kato stacks, and I take the push forward. At least assuming it has good finiteness property that is, say, perfect complex, then it will be a perfect complex of such objects, which is at least the kind of structures that you want to see if you want this to be related to Yodo-Kato. I will stop here.
Questions? Maybe I can ask. So, so this last part, X is living over FP, and I was wondering. So, in this picture of crystallization, so X living for FP. So this is something that, in particular, for a perfectoid space over FP, is producing something, and in particular, it's sort of determined by that. I was wondering if one can phrase this in terms of ring stacks, the sense that in terms of some sort of, well, there's some, so in the theory of crystallization, formal schemes, there's this ring stacks that I formulated in this notion of a ring stack. And I was wondering if this Yodo-Kato construction as a function from perfectoid spaces with to these Gelfand stacks can be phrased in terms of ring stacks. And there's some sort of nice.
Yes, I think you can. Okay. Maybe I need to think, but I think there is a way to formulate this definition in terms of exact. So you can write explicitly, like in fact, you can write a counter points description of the pseudo-Cato stack. So determined by what it does in the analytical timeline. Maybe it's better if I think before trying.
Thank Arthur-César again.